The arc-length integral is a fascinating tool from calculus that allows us to calculate how long a segment of a curve is. When I first learned about it, one of the first things I wanted to try plugging in was just x squared. Messing around with the integral in the back of class, during which I may or may not have missed out on the reasoning behind this amazing formula, I quickly realized that despite it looking pretty easy to solve, it's actually quite difficult to solve. When I even asked the teacher about the integral, she replied that it's too difficult to solve with basic calculus tools. While let down with this answer, I decided to keep trying anyway. As it turns out, we can solve this integral with just one basic tool. That is u-substitution. Some may be averse to, shall I say, using it. But honestly, it's better than integration by parts. Still, the final answer is slightly more complex than what it ought to be, but achieving it is a pretty nice exercise. We get to apply some of our favorite basic calculus tools. Alright, we can first see what expression we're working with. True sigmas know that the next step is one of the trigonometric substitutions. Previously, I tried dividing by x or something, but that doesn't work out. I don't even remember what I did. The substitution we deal with unfortunately does not have sine or cosine, which is pretty fun to deal with, but instead involves tangent and secant. One of the places trigonometric substitutions with tangent of x is useful for is with 1 plus x squared. The classic example being the integral of 1 over 1 plus x squared. The mechanism is that if we substitute x for tangent of u, then 1 plus x squared turns into secant of u, which is happy for everyone. In our example, obviously there's an extra 4, but it's not really an issue because we can set 2x to be tangent of u. We can then simplify. We get this equation. This isn't particularly nice for us because if we convert the secants to cosines, we see that the cosines are in the denominator. Usually, if the integrand is just a positive power of a cosine, that's pretty easy to deal with, but we don't have that here. However, once again, trigonometric identities come to rescue us. If we focus on trying to get rid of the trigonometric functions, we can put a cosine at the top and do away with a substitution. More precisely, we see that this right here is actually this, which means that we can substitute v to be sine of u. Next, we just kind of simplify stuff further. Now we get to use another tool from calculus, partial fractions. This part's kind of self-explanatory, so... Anyways, the result is this, which is very manageable. Once we integrate everything, we of course have to put everything back into terms of x. We can just solve for v in terms of x and call it a day. Well, actually, we can simplify a little bit here, but honestly, it doesn't really make it that much nicer, and I might make a dumb mistake somewhere, so I'm not doing it. You see very clearly that square root of 1 plus 4x squared is in a lot of places. To make sure this is right, we could either try differentiating it or just graphing it on a graphing calculator. Fortunately, this answer perfectly matches the integral. So that's our answer. The size of the expression, I think, really illustrates how integrals hate square roots and roots in general. Even for quite simple looking functions, their integrals can be quite complicated. The day I first encountered this integral, I actually tried plugging it into Wolfram Alpha and was dumbfounded by the result. Specifically this right here, since it's not covered in basic calculus. Only after much thinking did I finally arrive to the answer. Overall, I'm glad that I kept trying the problem. Even though progress was incremental, I still got to solve the problem in the end, which is great. I hope you also learned something from this video.